Silicon is one of the most essential elements in modern technology and is found in almost everything we use. But did you know it's the second most abundant element in the Earth's crust, making up more than 25% of the planet's composition? This seemingly ordinary mineral is actually the key behind some of the most important technological advancements of our time. China, for instance, is the largest producer of silicon, but significant reserves are also found in countries like Brazil and the United States. Its most well-known application is in the production of microchips, but silicon also plays a crucial role in renewable energy, especially in solar panels that are helping to transform the way we generate electricity. The price of silicon can vary widely, from just a few dollars per kilogram to hundreds, depending on its purity and intended use. Beyond electronics, this material is also used in glass and ceramics production, and even in cosmetics and pharmaceuticals. The process to purify silicon is long and costly, starting with the extraction of quartz, which must be subjected to extremely high temperatures to obtain pure silicon. This stage is critical because high-purity silicon is essential for producing high-performance chips and solar panels. Did you know that silicon chips are what allow devices like your phone or computer to process information at incredible speeds? If you're amazed by what silicon can do, get ready to discover every detail of this incredible process. And if you enjoy this kind of content, don't forget to subscribe, hit like, and share. Let's get started. Step 1. Quartz extraction, the starting point. The process of making silicon begins with a widely available natural resource, quartz. This mineral, composed almost entirely of silicon dioxide, CO2, is abundant in the Earth's crust, especially in silica sands and rocks like quartzite. To obtain high-purity silicon, it is essential to select quartz deposits with minimal impurities, such as iron, aluminum, or titanium. Quartz is generally extracted through open-pit mining. Rocks containing quartz are removed using heavy machinery, crushed, and transported to plants for an initial sorting process. During this stage, fragments with visible contaminants are removed, and materials are classified according to size and composition. Once collected and sorted, the quartz undergoes washing and drying to eliminate unwanted particles. This step is critical to ensure that the base material is pure enough to continue with the transformation process. The quality of the extracted quartz directly impacts the efficiency and cost of the subsequent stages. Without proper raw material, it is impossible to obtain the ultra-pure silicon required for manufacturing microchips, solar panels, or specialized glass. Step 2. Converting quartz into metallic silicon. Once the purified quartz is obtained, the next step is to convert it into metallic silicon, also known as metallurgical-grade silicon. This process involves a high-temperature chemical reaction that separates the oxygen from silicon dioxide, CO2, releasing silicon in its elemental form. The conversion takes place in electric arc furnaces, where quartz is mixed with a reducing agent, usually carbon in the form of coke or wood. When temperatures reach around 2000 degrees Celsius 3632 degrees Fahrenheit, the carbon reacts with the oxygen in the quartz, producing carbon monoxide, CO, and leaving behind molten silicon. The molten silicon is collected at the base of the furnace and then solidified in molds for transport. At this stage, the silicon has a purity of around 98 to 99%, which is sufficient for general industrial applications but still inadequate for electronic devices or solar panels. This metallurgical-grade silicon serves as the foundation for a much more rigorous purification stage later on. Converting quartz into metallic silicon is energy-intensive, but it is absolutely essential to produce the ultra-pure silicon required by the technology industry. Step 3. Purification using the Siemens process. For silicon to be used in electronic and solar applications, it must reach an extremely high level of purity, over 99.9999%, known as electronic-grade silicon. To achieve this, an industrial method called the Siemens process is used, which transforms metallurgical-grade silicon into ultra-pure silicon. The first step of this process involves reacting metallic silicon with hydrogen chloride, HCl, at temperatures between 300 and 350 degrees Celsius, 572 to 662 degrees Fahrenheit. This reaction produces trichlorosilane, CHCl3, a volatile gas that can be easily separated from the metallic impurities present in the original silicon. Next, the trichlorosilane is purified through fractional distillation, removing any remaining contaminants. Once purified, It is introduced into a vertical reactor heated to nearly 1,100 degrees Celsius (2012 degrees Fahrenheit), where it decomposes in the presence of preheated silicon filaments. The result: silicon deposits layer by layer onto these filaments, forming ultrapure silicon bars, known as polycrystalline ingots. This method can take several days but produces one of the purest materials on the planet. The resulting silicon is ready to be molded into single crystal structures, which will be used to manufacture electronic chips, photovoltaic cells, or high-precision optical components. Step 4. Crystal growth, the Czochralski method. Once ultrapure silicon is obtained, the next step is to turn it into a single, continuous crystal, ideal for manufacturing microchips and solar cells. To achieve this, the Czochralski method is used, a technique developed in 1916 and widely adopted by the modern tech industry. The process begins by melting the ultrapure silicon in a quartz crucible at a temperature of approximately 1,420 degrees Celsius (2,588 degrees Fahrenheit). Then, a crystalline seed, a small piece of silicon with a defined crystal structure, is carefully introduced into the molten silicon. The seed is slowly rotated and pulled upward in a controlled manner while remaining in contact with the molten silicon. As it is drawn out, the silicon solidifies following the structural orientation of the seed, forming a cylindrical single crystal ingot. These ingots can reach several meters in length and diameters of up to 300 millimeters, 12 inches, or more. The structural uniformity of this crystal is essential to ensure the performance and stability of electronic circuits. The Czochralski method is complex, costly, and slow, but indispensable for producing silicon with the electronic properties required. From this ingot, thin silicon wafers will be sliced, which serve as the foundation for chips, solar panels, and high-precision sensors. Step 5. Cutting silicon wafers. Once the single crystal silicon ingot has been formed using the Czochralski method, the next step is to transform it into thin slices known as wafers, which will serve as the physical foundation for chips and solar cells. The ingot is first ground and polished to achieve a perfect, uniform cylindrical shape. Then, it is sliced into extremely thin wafers using a diamond wire saw, allowing for precise cuts with a thickness typically between 150 and 200 micrometers. This process must be performed with extreme care to prevent cracks or warping. After slicing, the wafers undergo chemical and mechanical polishing, removing surface irregularities and leaving them perfectly smooth. Some wafers are also marked with orientation indicators to guide later steps in microcircuit fabrication. The quality of cutting and polishing directly affects the final product's performance. Even a microscopic defect on a wafer can compromise thousands of chips in a single production batch. These wafers are now ready to move on to the doping and photolithography process, where electrical functions are defined, enabling the creation of electronic devices, solar panels, or high-precision sensors. Step 6. Doping and processing the wafers. Once the silicon wafers have been cut and polished, they undergo a crucial process to turn them into actual electronic components: doping. This step involves introducing small amounts of chemical elements into the silicon to modify its electrical conductivity, creating N-type, negative, or P-type, positive, regions. The most common dopants are phosphorus, boron, arsenic, and antimony. These are applied using techniques such as thermal diffusion, ion implantation, or vapor phase deposition. Each method offers different levels of precision and penetration depth, depending on the design of the device. After doping, the wafers go through multiple additional processes, including oxidation, photolithography, chemical etching, and deposition of conductive layers. These steps create the tiny circuits that make a chip, solar cell, or sensor function. For chips, these treatments may be repeated dozens of times on the same wafer, building complex electronic systems in microscopic layers. Each wafer can contain hundreds or even thousands of individual chips, which are later separated and packaged. This is the stage where silicon transforms from a simple conductive material into the heart of modern technology. Step 7. Final applications: chips, solar panels, and glass. After the complex processes of extraction, purification, crystallization, and doping, silicon is finally ready to fulfill its role in a variety of essential modern technologies. First, doped silicon becomes the foundation of millions of microchips used in computers, smartphones, smart appliances, cars, and virtually every electronic device. Each chip contains millions, or even billions, of tiny transistors that process information at incredible speeds. Another major application of silicon is in the production of photovoltaic solar panels. Silicon wafers convert sunlight into electricity through the photoelectric effect. These panels are key to the transition to clean energy, powering homes, industries, and even satellites. Lastly, although less high-tech, silicon is also used to manufacture heat-resistant glass and ceramics, highly valued in laboratories, kitchens, and construction. In these cases, fused silica or mixtures of silicon dioxide with other minerals are used. From a simple quartz mineral to complex electronic devices, silicon undergoes an amazing transformation. It's the silent but indispensable element that drives the digital, energy, and technological revolution of the 21st century. And that concludes the fascinating journey of silicon, from a single grain of quartz to the core of our devices, solar panels, and even the glass around us. A complex process, yet vital for the modern world. Now a question for you. Did you know that so much work goes into a single element behind your smartphone? Leave your answer in the comments and tell me which part of the process surprised you the most. If you enjoyed this video, give it a like, subscribe, and share it. See you on the next journey into the heart of technology.